Okay.
Are you ready? Well, it is all about making it work on a small scale.
Yep.
It's all about making it work on a small scale.
Hello, guys.
Yeah, our presentation is on the Heebie Jeebies. And the challenge was to design and run in simulation a drone which could fly around the International Space Station. So potentially quite different to your Earth-based drones, as there's no gravity. It needs to be able to maneuver around, not damage anything. Hopefully have the ability to navigate autonomously, because the main application for this drone would be to deliver items to astronauts who might be working in one area of the space station. This thing will be able to go and pick some stuff up and bring it back to them. And in the scope it says items up to about 2 kilograms. So there was a previous project which was built by NASA, the Spheres project, which had flying items on the space station. So there's a few of them there. And these were implemented using gas thrusters, and they're capable of moving, rotating, because they have 12 thrusters on board and translating around the station. And they have some autonomous capability using ultrasonic detectors, but beyond that they're pretty limited. They didn't really have much use, possibly for some experiments, but that's about it. So we wanted to come up with a new design that would fulfill this range of criteria, and we brainstormed quite a lot of wacky ideas, but in the end settled upon combining two relatively established features, robotic products, a quadcopter and a robotic arm, but to make a novel product. So this is what we designed. It's got the rotors at one end, which are capable of forward and reverse thrust, because you need to slow yourself down, sort of speeding up when you're trying zero gravity. It's going to have this joint section, which is capable of moving up to a 90 degrees angle, which has some benefits we'll talk about later, and a gripper section at the end for collecting items. And it will have cameras as well as lateral proximity sensors at the front and the back for navigation and picking up objects. So we want this to be a modular device where these can be separated and changed depending on the needs of the astronauts or as new designs are developed. So the gripper, one idea we had would be sort of flexible gripper inspired by this one from Festo, where it can pick up a whole different range of things just by changing its shape and mounting it at the end of the device like this. We think we'll have a very versatile range of what we can pick up in the space station and probably far greatly exceed the 2 kilogram limit that we were told to design for. Yeah, so the joint section, like I said, can move into this orientation and also rotate 360 degrees around here, which is able to make small adjustments when we're going to grip items, but also for control. We'll open up a whole new range of possibilities for flying the drone. So we can use the quad rotor to change the axis in sort of similar ways to you would on Earth. But also by rotating the joint, we can move the entire structure of the thing because of the angular momentum that it generates. Or by moving this into the other orientation, we can then start rotating about the object you have on the end by the moment of inertia of this object. You can start manipulating in all kinds of new ways for it. Yeah. So the second half of the challenge for us was moving that model into simulation, and we used this gazebo simulator, which uses the robot operating system, and we've been trying to get the model to fly around in there. We had to adapt the simulator to work in zero gravity because it's an existing product which just can provide robotic simulations on the ground. We had some difficulties getting it to work, but eventually we did manage to get our model into the simulation, but due to some scaling problems, it was actually bigger than the model of the space station, so we couldn't fit it in. But if we just have a little more time, we might put it to work. Well, we've got this, which is AR drone, which is similar as it's a quadcopter, but this doesn't have the arm on, which, sorry for the poor quality, we have flying through this section of the space station, just demonstrating roughly how it would work. Yeah, that's pretty much it.
How efficient are propellers in space?
Well, on the station they're just it's slightly less pressurized. I don't actually know the air pressure within the station, but they would work in the same way as on Earth, and you only need to give it a little bit of speed initially, and then the propeller can turn off. So we weren't so worried about having them in terms of like crashing into things because they won't be running for quite a lot of the time. We just give it some initial momentum.
So if you are in zero gravity, then your drone will, well, maybe will go one way, and the whole environment will go the other way. How do you stabilize that? Because you have this gripper, right? And you would have to somewhat correct the movement of the environment. So it could be that the space station or shuttle or whatever is rotating in a different direction. How would you stabilize it with the hardware?
Well, we have two cameras, one in front to see the different kind of grippers that you can use, and one in the back as a tech position. And with the joint, we are expecting to have more weight in front, so it will have a smooth movement. So because you can have like different degrees of freedom, you can establish even if the environment is moving, and because you have more weight in the front, the movement is more stable. The only problem could be maybe torque that you need, but the movement is maybe not the strongest.
I mean, most of the time it's not going to matter what its orientation is to the rest of the station, because anyway it can be picking up objects and it's going to be manoeuvring to pick up those objects and turning the arm to lock onto those anyway. So it's going to be adjusting itself to get into position.
What happens if the device, I know it's not supposed to crash into anything, but what if it's knocked by an astronaut? It sends itself in there.
Well, it should be able to pick up that. We want it to have autonomous flight capability, so you're using the camera, it would be able to notice that it's suddenly veering off course and hopefully take evasive action. Also, yeah, well, the lateral proximity sensors might pick up that because if we have we're envisaging a front and rear facing camera, but I mean, that could be modified, but we can detect if it's going to hit something on the side. Yeah.
I was wondering, could you show your picture of the drone, please?
Yeah.
A question about it. Yeah, the whole thing, maybe. So yeah, I was just wondering if you could give an intuition about why you chose this particular shape. Because the center of mass is going to be somewhere between the plane of those propellers and somewhere along that arm. And then when you're grabbing something, the center of mass is going to be even further down that arm. And I wondered why choose this design? Or what my intuition would be, it might be more favorable to have a center of mass right in between those propellers for moving and twisting in 3 dimensions, which you'll need to do. But is my intuition wrong there? Like, why have you chosen this design?
Well, I think partly is you just pick something at the start and you design it around it, so you could make it work in that way. But what we envisaged was having the bulk of the mass at this end, so you can kind of have that as the more stable part of the device and move the propellers around that without too much movement of the gripper. And that allows you to pick up an item and then immediately direct your blades whichever way you want to go and just drive off in that direction. So we very much consciously designed it with the idea that this end would have most of the weight.
So you use gazebo as a simulator and you adapt it for the ISS zero gravity.
Yeah, that's.
How did you do that modification?
It's got built-in gravity settings, which we actually tried removing entirely. But this is going to be used for working out your acceleration than completely metal. So we have to keep a very small value in there. But by and large, we've reduced it right down as far as possible, while still getting the simulator to still work and function properly without crazy.
So do you have any guarantees that gazebo will work as a simulator in zero gravity? Or has it been built for that and you don't know what's going to happen in the limit? As you say, you need to keep a very small value. You know how robust that simulator is.
It's not, I think even in the documentation I've got for it, they're saying it's not as advanced as it should be. It models the whole thing with a block, so it doesn't look at individual, we've talked about torque on the plans, model individual torque on the plan. It's just, if you want to move up, you tell it to move up. It was a calculation based against gravity and wind resistance to put into the system and tries to move the entire block. So it was adjusting that without taking apart the entire navigation section, which we didn't have time for. It wasn't possible to change the values that were going into that calculation. I think we did have a go at them to reach a pilot at any point to try and get it to run. Sometime in the early hours yesterday. So
It's quite as guys.
yeah, it's still yeah. So it's quite. We pushed it. I think we pushed it as far as we could go without stripping it right down and looking at the simulator and changing it entirely.
Okay, thank you very much.